recipes. There's a little bit of repetition, but we want you to be able to repeat it. So I think at the end of this concepts Adam showed yesterday are then all familiar. And so a couple of tips and tricks. I'm in front of, I'm a short story reader, so I called it cookbook style. It's a little story, couple of simple recipes which you can apply easily and independently.
And
so
one quick question.
When if you, yeah, go ahead.
Yep. Should I interrupt during your presentation to when someone asks something to push the question to you?
We can do that. I'm not filling the entire slot. I think from the timing, I guess we will have a couple of more minutes at the end.
Yeah.
We can do that.
Yeah.
Yes. Shall we start? Wang, what do you say?
I think we still have quite much less attendees than yesterday. So I think we give it, they say 3 minutes more.
Mm-hmm.
I mean, in the meantime, we can also start answering one question here in the chat box. Someone, I think Daniel, asked about PyTorch allow develop multi-GPU system. Why should we prefer Hoverot?
So if you love PyTorch, you have the choice to use Hoverot. You also have the choice to use what's built in the data parallel method. Both come down to leverage a good networking infrastructure and communication infrastructure, which is important. So technically, both come down to the same.
You even have a wider choice because you also have Apex. Yes.
Even that,
for
yes.
PyTorch. Yeah. Which has, but they are all semi-identical behind the scenes.
Mm-hmm.
In a sense,
so it's kind of a preference.
We've tested Horovod at a very large scale, so we know that it will work. And it also has some advanced features that some of those other implementations don't, like gradient compression, gradient batching, ability to use a bit of machine learning to understand how to batch gradients for communication. It has some advantages, but if you're proficient with PyTorch implementation and you're not seeing degradation of performance between 1, 2, 4, 8 GPUs, stick to that. Anything else? Okay.
So I'm using both. I'm using the Horovod way for PyTorch and the PyTorch, the native PyTorch.
Yeah.
Adam was mentioning Apex, which is a library for mixed precision, making mixed precision simpler. And in PyTorch 1.6, the concept of mixed precision is now a native concept. And so if you are going with data parallel, for example, then this harmonizes basically out of the box. And so I gave that a try and it works like a charm.
Is
All
there
right.
a parallel framework for low-level kits such as Kublas? Yes, but that's very out of scope, quite out of scope of what we're discussing today. Mm-hmm. We've been discussing yesterday. Yeah.
You can hear me well. I would say.
But...
Yeah, sorry, it was late.
No,
I would say I get started. Okay, Wang?
Yes, there is one question. If you want to take now or later.
Okay. I don't have the chat window open, but we can take it now.
So I think I've answered it. Is there a parallel framework for low-level kits such as Kublas? Yes, you can, and people do use libraries such as Kublas in a distributed manner, but it's very substantially out of scope of what we're discussing today. We should take it offline.
Mhm. All right.
Yeah. So
Then I slowly get started.
yes, please go ahead, Adolf.
Yes.
Yeah.
Welcome once again to the second part of that one. My name is Adolf. I'm a colleague to Adam. You have the email addresses on the screen of the both of us. Don't hesitate to contact us. And I am a solution architect, and we make sure that these innovations are going to be used to the benefit of the customers. Today we have similar content than yesterday, but from looking at it from a practical point of view. I do have a little motivation. We all face rising data sets. Yesterday, Adam explained data sets are expensive. We have more clever alternatives, but the data sets are rising. I'm specifically taking care of one vertical, the automotive domain, and nobody in the automotive domain has stopped collecting data. So they still are collecting data, making the existing solutions better and better. So what is the classical approach? We do mini batching, we do stochastic gradient descent, and usually we make a memory bound problem out of it. But what does more data mean? More data means more work. There's another interesting aspect coming into play. At the same time, looking at, for example, computer vision, cameras, all sensors get better resolution. So there are two trends overlaying here. One is the data set is rising and the data quality is going up. And that ultimately means even more data. Now, what does it mean for a memory bound problem? Our batches get slower. And ultimately, this means we're losing control over our innovation cycles. So just the typical nature of the project means we are losing control over the innovation cycles. What can we do about it? And now let's talk about a few innovations to gain back control over the innovation cycle or the turnaround time. Well, you're used to big memories now. I have it in that slide because it is a difference. Memory makes a difference. So 32 gigabytes are standard kind of everywhere where we look. If you take some service from the cloud, 32 gigabit is what you get, but that goes on, right? In the meantime, we have 80. So memory has a value because it increases our batch size. That's one innovation. It's just a bigger hammer, right? Nothing very specific. But now think about how can we make even more progress? How can we increase basically the batch sizes? One thing what we didn't talk about yesterday, but what might be a good follow-up topic is mixed precisions. You can do a lot of the computation in smaller precision. Not everything needs to go in FP32, and you can do a lot in FP16. And this is a topic which saves the memory, which has a benefit for the batch size. So that's an innovation you don't want to miss, because in most cases you easily double the output of your infrastructure investments by a factor of 2. So this is important. Adam made a comment yesterday. The best research papers or the top ranks of the research is done by people who have a lot of compute available. And so it's if you want to get into that league, make the best out of your infrastructure. So then multi-GPU and multi-node. So essentially we put more of those components side by side. And then here I try to visualize this is the way to get back control over the innovation cycle. Right. Now, yesterday we did not talk about a technology to connect the GPUs. We mentioned there is one, which is called NVSwitch in the meantime. NVLink is the first generation of that one. But this is kind of a necessity for that one. So that's basically the fourth innovation to make this concept work and scale. Kind of all my customers are facing this. this problem. Okay, let's jump into it. I go straight into it. In the meantime, there's much better material out there, but when I first need to look at it, there was not too much material out there, and now we are in the comfort zone that it is kind of mainstream. Sometimes people are have a misperception. If many people go on a more powerful system and they start up TensorFlow, then it lists up all the GPU resources, and then it creates the illusion that you're using all those. But very often it behaves like a small child at the table. And I compare it with my young boy. And if he's on the table, he likes to fill his plate with more stuff that he can consume. And that was the default behavior from TensorFlow. So basically allocate everything, but only eat a little bit. Same with Keras. Now what do I have on this chart here? This chart is an architecture of a multi GPU system, and all those blue boxes, they mean there's a GPU, right? In total, in this system, we have 8 GPUs, and that's a classic architecture. And then we have 2 CPUs. It's a multi-core system. So in essence, we want all the resources to be used to the full extent. That is what we are aiming for. Now we have the frameworks which make it more simple, but still that happens. Not so often anymore, but it can happen. So watch out. When you start up one of those frameworks, they tell those are the resources I have, but in almost all cases, they use just one of them. Adam showed the tricks yesterday, and I repeat the tricks as well. So in essence, we want to have all the GPUs running, and we also want to have a balanced system. That means there is no bottleneck in between which slows down something. In that system, there's something missing. There is the NVLink missing. Now recall what we heard yesterday. All the GPUs, the concept which was introduced yesterday was each GPU runs in a known process. It needs to share its findings with the other process, with the other processes. That's the right term. That means they all need to communicate each other. And here, the violet color and the arrows mean they are attached via the PCI switch. That's a classic architecture. When you plug in a GPU, it sits on the PCI bus. That's very classic. In the meantime, we have PCI Gen 4, which is also a pretty good beast, but conceptually all is right. So without an NVLink, there's no direct connection, right? How can a GPU 0 communicate with a GPU 7, for example, 5, you choose? Well, it basically goes down that path from one CPU via the other, goes into the PCI switch complex again. That's round trip. And this is what needs to be avoided. In the meantime, this is completely switched. In our first system, there was kind of a hyper mesh, kind of pretty decent connect. Now it's even better. Now what is good here? Some of the communication goes direct from GPU to GPU. And there's a library called NCCL, we call it Nickel, which is taking care of that one. So it happens usually behind the scenes. So Nickel can make the best out of your system. It discovers the architecture and says, there's a better connection than the PCI bus. There's a better connection than a TCP/IP connection between two systems. For example, there is an InfiniBand connection. So this is a library which takes care of the infrastructure related part. If you have a 2 GPU job, it discovers the best connection between the GPUs in the system. If you have a multi-node job, it discovers the best way to connect to them. It can fall back to PCI, it can fall back to TCP. It tells you this. It's important to understand sometimes, but it basically takes away infrastructure responsibility from the user, which is good. So in essence, we want to have a balanced system. We want the red is basically feeding the data in. The blue is basically exchanging the gradients among the workers. So now you understand that this infrastructure is there for a reason. Let's go quickly through Horowat once again. I call it recipe number 1. Press the sport button. Think you sit in the car and then you say, I want to go faster. Press the faster button. You need to import it. We can go straight through it. You keep your model. You don't change anything on your model. That's important. I want to emphasize this again. But you program your program kind of the same as it is a single GPU program again. And this is what makes this approach so so elegant. So just recall from yesterday, you need to import it, you need to init it. That's a no-brainer. Usually you are having your optimizer. Now let's call your optimizer what you have as a per tower optimizer. You find the terminology of tower in the context of multi-GPU often. It means one process or one worker. But you're introducing a global optimizer, so to say, which is also the synchronization point between the workers. Just recall yesterday it was called HVD the optimizer, and you introduced that one. So this is the distributed optimizer, which acts basically as the synchronization point between all the workers. That's just repetition from yesterday. In order to prepare the system, you need to do a little bit of housekeeping. Here we are using the TF-Train monitored training session, which is a TF1 construct, but all the hooks and that stuff remains when you go to the TF2 construct as well. So the data loader stays the same and the hooking as well. So remember, TensorFlow is greedy. We need to tell TensorFlow you only consume one GPU. And this is what we're doing with the visible devices. And we tell it which GPU it's allowed to see. I'm going to spend a few words on the rank enumeration, because each GPU only gets to see each process only gets to see its corresponding GPU. So a local rank is basically enumerating all the used GPUs on this system. There's another rank which is used when you work on a multi-node system. Recall checkpointing and logging. Adam explained it yesterday. Checkpointing and logging is something you do on one system only. Otherwise, they write the same stuff over and over. That only leads to write conflicts on the target destination, but there's nothing wrong about it. The batch size. We talked about the batch size yesterday. Here you see in line 98, this is a per worker batch size. So the more towers, the more processors I have, the higher the batch size is linearly. Right, and then we are about to train. We have to have a stop condition to see when it stops. So we don't enumerate typically epochs and steps in the epoch. We have a stop condition, and then we organize usually the warm-up rates and the learning rate not based on an epoch size, but on a global step size, because this is what all the workers see here. And we do this because we have a stop condition like this, which does a graceful stop among all the workers. So you see, not a lot has changed. Typically, we have a session opening in the TF1 world. Now this is basically monitored training session, and then the handle we get. This is the handle for it. We use basically the same syntax and the same call in here on the run on this change session. So not a lot of things. I think when you count it down, it's kind of 7 lines of code to change in the basic thing. So it comes very cheap. Now what happens? Typically now your bottleneck, your new bottleneck is hopefully the data pipeline. And sometimes there are a few other things to check. For example, I was running one time into a memory imbalance. And so the checkpoint writer was consuming a little bit more memory. And it was a bit of a pity because I needed to be below this threshold, and then it led to an inefficient use of the memory of the other workers. So have a check, but I think this behavior is gone in the meantime. Right, that was a very quick repetition of Horvath and simplicity. I call it the iPhone experience to multi-GPU. A few words on the on towers, ranks, local ranks. So in gray, you have a process. Each process has its own data pipeline. I've made read and augment. I wrote that in here. That's the read and augmentation loop for the data. It queues up the data, and then the training loop is picking it out from here. Each process has the same thing. Each process has its individual data pipeline. I repeat it because in the early days of TensorFlow multi-GPU, you could have built a shared pipeline serving multiple GPUs. And when you do, for example, the TensorFlow mirrored strategy, you have one process with a joint pipeline serving multiple GPUs. So there is this little difference when you have those two architectures. So here we stick in the simple world, one process, one GPU, one tower, and the processes are the same. So a few things are different between them, and we get into this one because when we're doing the log writing, for example, the checkpointing, one has to do it, right? One of those guys has to do it. And we decide basically who is doing it basically on the rank. And when those things are started up, they get a rank assigned. Here in red, I've made this synchronization line between those processes, which is introduced by the distributed optimizer. Right, so I hope this is clear. Now a word on the rank enumeration. When you start up Horvath, it has a couple of parameters for you. You can ask for those parameters. You can type in HVD size, and then it gives you the total amount of workers it spins up. That's very familiar to the MPI guys because they use the same thing. I tell you in a minute why you need to know it. Then you can ask, what is my individual rank? This is important to pick the right piece of data. And as said, basically we decide on the rank on special housekeeping tasks. Typically rank 0 is doing checkpointing and log writing. Now there's a little pitfall. There's a local rank. And this can be not unique when, no, this is not unique when you do multi-node jobs. So think about, you have two systems, each has 8 GPUs. Then the local rank on the first system goes from 0 to 7. The local rank on the second system goes from 0 to 7. but the rank goes from 0 to 15 in total. So that is introduced because sometimes you want to do special housekeeping on a per system basis, and this is the reason why this one is there. So let's say we call up a job like this with 4 GPUs. It comes down to 4 processes. This is actually a visualization of 4 GPUs across 2 systems, across 2 nodes. So each of them, think about 2 powerful workstations, for example. And then the job where we started this from on the same system has the local rank 0 and the rank 0. And the next job close to it has rank definitely local rank 1, not necessarily. It can be also a different rank. It depends on the startup behavior, but that's a simple visualization of it. So basically, rank counts from 0 to the amount of workers minus 1, 1, 2, 3. However, local rank counts just to the maximum amount of the workers available on the system. All right, just in case you run into it, and the overall size, what the Horovod is reporting here is 4, obviously. Just to make that clear. Now a little quiz. Let's assume we have those 4 workers as in the slide before. And the green is the gradient. When we start our multi-GPU job and all the 4 systems report the same gradient, what does that mean? I don't see the chat at the moment. Ah, yes, here's my chat. No, nobody? Just recall, Adam explained it yesterday. Each system is doing the gradient descent, and then we're doing the average on the loss, and then step by step backwards. If each system reports basically the same finding, then we've done something wrong with the data, because if each system is going to see the same data, then it literally comes down to just increasing the learning rate. So that's a little quiz. I want to motivate it, how to work with the data. I do it because in many samples, you likely going to use this week, or you download from somewhere. People don't speak a lot about the data pipeline. Let's talk about improving the data pipeline. So those are the 2 mechanical things you need to do. So in the most cases, when I get more demand, or the GPUs get more demand and work more, then the CPU needs to get more data, obviously. But it's not about the more, it's also about who sees what. And I want to introduce the concept of sharding. Because the perfect thing was for each epoch, we're doing a complete shuffle. But we don't do this actually, because shuffle on a global data set would be expensive. So what we're going to do, we're on the fly assigning basically a part of the data to a worker. And one of the most common schemes is that this is happening in a round robin manner, for example, with a simple modulo calculation. Another best practice thing with what is done is you use, we call it a director file. Let's say this is a list of frames you're going to load, and then it's easier to do basically the shuffling on the director file, which is, think about it as a pointer list, so to say, rather than shuffling a big data set. And that makes it very easy to select in a more random fashion. So actually, we don't compile a per worker data set and create this data set and copy it there. That's not worth the time actually, and it's not convenient. So that best practice is to do that concept always on the fly. One of the most seen processes is you have your data record. It can be a file name, it can be just a line name, for example. You hash it, and then you make a modular calculation and say, okay, this one belongs to or equals basically the remainder equals my rank number, and then I take it. Otherwise, I throw it away. So that's a simple round robin scheme. The other little topic, it's still there, not so often anymore, but session run and feed dict is a concept which is expensive because there's a NumPy to a TensorFlow graph conversion going on, and this is expensive. So whenever you see this one, try to avoid it. So let's give a sample about a data sharding. Data sharding, and here I was using a couple of months back a segmentation problem, and what you can see here in this right is basically two passes: a pass for the image and a pass for the ground truth. So this is a comma separated a pair here, and they belong together. And actually what we are going to do here is to say, well, one has to take care of all the elements with the remainder of 0. The other has to take care of the elements with the remainder 1, and so on, depending on how many GPUs we have. In that sample, we say, let's have 2 GPUs here. How does it look like? So we have a rank of 0 and a rank of 1. Then we apply the concept before, and let's say we are GPU 0, then 0 modulo 0 means 0, 2 modulo 0 means 0, and so on. So those are the non-red parts are the ones the GPU 0 picks. Very easy concept. So you find it kind of almost in many samples. Let's say we have 3 GPUs. I'm still GPU 0, but then what happens if I apply the same calculation? Then I have one more rank, and so I'm picking only the zeros, the third, the sixth, and so on. The GPU, the worker one with rank 1, that's basically the next, and so on. So you see, it's an easy concept which does not require coordination among them, and that's the main thing. You don't need to do data partitioning and the data preloading. That's one of the most seen concepts. And the other concept is to make a pipeline, the loading better. And I've picked one of the earlier samples, and so I've seen a big improvement, for example, with TF record. That's now more or less hidden by the TF dataset API, which can still handle TF records. The thing what you should take away is there are better representations than a file-by-file manner for each entity you want to load. And often this is a serialized format. And the beauty at that time of TF record was you can what you load directly ends up on the compute graph in TensorFlow. It is a bit of creating your data set, because you here it required grouping my ground truths and my image label images into a serialized data set, and I had to define a couple of tags and so on. But takeaway, it is a good practice to use serialized data formats. They can speed up training a lot. The thing what I use today is I use serialized data formats, but I let them load by a library called DALI, which is also an interesting framework accelerating the data pipeline. So the loading is a little bit different then, and I had to define a function which is basically delivering me TensorFlow placeholders for images and labels straight, rather than delivering me, for example, NumPy arrays. So when you work with those, then you are handing into TensorFlow objects and to feed them straight into the graph. It's a good concept, and which makes sense. There are other serialized formats as well, so this is not the only one. But takeaway, think about those. And then what is getting a little bit different sometimes is that you define a thread runner, but now dataset API hides that as well. But this is an important thing. Now in a system we have more GPUs working. That means our data pipeline has to work quicker, and that ultimately leads to the concept of multi-threading. The CPUs what we have in our latest DGX A100 has a huge amount of cores, and they are ideal to perform this augmentation work and the parallel training works, train data loading. So in other words, use those libraries and the small library type. Don't use, when you can avoid it, for example, libraries like OpenCV. They are very good, but they are not made for performance. They are made for functionality and good usability. But in those contexts, we've seen that they not accelerate basically the pipeline. So if there is a way to implement the augmentation function with the native functions, then take them, or take DALI. Very good. So those are a few recipes to accelerate your data pipeline. We talked about sharding. Kind of all data loading APIs have a sharding function. DALI has, TensorFlow dataset API has, what's the name from PyTorch? But I was using one in PyTorch as well. So that's a standard concept. I told you about the parameters HVD size and HVD rank. Those are the two parameters you use to basically do this round robin picking here, and I made them in bold. So those are the two useful parameters to say this worker takes about those data set and the other one takes about that one. So you see how that that fits together. You can do local rank, but I don't advise it, because when you scale out your job on a system or on two systems, and each system can just have one GPU, then this concept is not going to work, right? Think about it. Rank is the right parameter. Local rank is there for doing some housekeeping jobs per system. Right. I had a sample for the sharding from the dataset API, and I need to look into the line, and the proper line is around here where I have my mouse pointer. So here it's basically done in the pipeline. The reason I bring up basically this data loading pipeline here is, of course, we need to load the data, right? We need to apply the sharding, and it's kind of logical. Do sharding as early as possible, because you don't need to invest CPU cycles or GPU cycles to do augmentation and decide after complex augmentation to skip it away, right? So recipe here is sharding as early as possible. And when you have a director file saying please load this pair. And then you do the sharding basically on the director file, and you only load what is subject to be processed. A word on those on the thread count. Many of those APIs, and for example here this map operation is running in parallel when you allow it. And so if you go to the pipeline, then you find a lot of parameters with regards to the thread amount. And here you see basically it allows to take 16 CPU threads at this time. So think about it. You can play with it. Recently, I had a sample code where it still was one, and obviously that does not give you the best performance on a powerful system. So check it out, what the amount of thread it is. You can basically divide it down and assign it for each worker. You can also overcommit a little bit. Let's be fair. We don't do multi-GPU compute because it is just for fun. We want to get our stuff done quicker, the turnaround time. And if we do the same thing with the same hyperparameter set, then this doesn't work out, right? So one recipe you heard yesterday was you adjust the learning rate. That's plausible because when you have bigger batches, and we have virtual bigger batches in multi-GPU compute, we ultimately have less steps. Now think about that you are standing in the garden, and your optimum, your little pond in the garden, is in the opposite corner. You need to get to it somehow. And if you're running in 2 small steps, you have no chance to do it. So that's a simple metaphor to explain it. We need to adjust basically the step size. Now, Grzywaczewski in 2014 was already expressing a relationship between the learning rate and the batch size, and his recommendation was you scale the batch size by a factor of k, then you scale the learning rate by a factor of square root of k. If you open up Horovod, then you find linear scaling there. But the truth depends on the data set you're running, but that gives you a good corridor. Okay, this is what I would say is the mechanics of multi-GPU compute. So when you've done that, fine. My recommendation is also establish each and every project you start with it. And also take one of the projects you have and turn it into. So the changes, what I've talked about, what Adam talked about yesterday, it's a couple of lines, right? Give it a try and get it in place, and then let's observe it. So those are a few topics on. Let's look on the system and say it's good, it's not good, it needs improvement. How do you observe a system while it is training? I think most of you know the command and NVIDIA SMI, which is up here, which shows unutilization. It's a fairly basic command, but it already gets you to a good place. So typically when I reach more than 85%, I say, okay, that's kind of good. Some fine tuning might apply. That's already good, but you don't need to think about it too much. A good reflex or a good reaction to it is, okay, let's check how the CPU utilization is. Sometimes your model is also a bit limited, and that can also come down to a compute versus communication time, right? If the model is too shallow, too small, then the compute time is getting smaller and the communication time relatively bigger. So that can happen. So when I'm not happy if I see below 70%, I'm definitely not happy. Often that comes together when the CPU is basically very utilized, or a few threads of the CPU are very utilized. And that basically is an indication that the data pipeline and augmentation is too CPU intensive, or there are too few CPU threads. So that's a good indication. So that's not rocket science, but it gives you a feeling where to look at. Low GPU and low CPU utilization, that indicates more of an I/O problem, and so it might indicate a bottleneck of loading the data. Sometimes it also indicates that your cache is not working. The best practice, what we do is we enable caching of the data in the system, because we have this many epochs and jobs are going to see the data over and over again. So this is cache-friendly data access paradigm. So check if the caches are working, and yeah, maybe you need a system administrator to it, but it's not very sophisticated. We also sometimes see oscillating utilization. So obviously you need to observe NVIDIA SMI in a continuous way, or GPU top or NV top. And then also observe if this oscillation has an effect on the CPU. I've seen this behavior when nickel was not working. So the gradient exchange was done on a non-ideal path. For example, two big gradients going through the PCI bus, being aggregated by the CPU and not aggregated by the GPU. Also, I've seen this when my data loading is not happening in parallel to the GPU work. So when you feed the GPU, then the CPU should work on the next data batch. And today's pipeline frameworks, they do it, they work in parallel, but in older code, you see basically manual processing. So that basically means either one of the two is working, but not both at the same time. When you think your data pipeline is the issue, then my typical reflex is I make an empty numpy or an empty placeholder or random placeholder, and I feed this in straight into the model. So basically, I cut off the data loading, and that is a very easy way to understand if the data pipeline is an issue. And so it's basically detaching the pipeline from the model, so to say, and just observe the model computation. And I have seen then some models. I had some other bottleneck, but it wasn't a data loading bottleneck. If you do it, and if you see that the utilization goes up, then obviously you can blame the data pipeline and focus your work on that one. NVIDIA SMI can tell you something about the communication between the individual GPUs. You can use it for debug issues, or just for curiosity, but you can observe the communication between the individual GPUs, and that's a simple way to do it. You define a metric to measure in or outbound or the overall traffic, and then you can report it like this. So then you see what amount of traffic is communicated between each and every worker. We did mention multi-node compute, but we didn't say a lot about how does it work. You've seen yesterday with the MPI run or with Hohl run, we're kicking off those jobs, and we do the same thing on a multi-node system, so that's all the same. We need to create authentication credentials so that MPI run can log into the other system. But what happens behind the scenes is the communication between each GPU has to be done and has to be solved. And again, NCCL is coming into the game, and you can observe how it is running. So this is an example where we have 8 GPU systems. In total, we have then 16 GPUs in that workload. And then now Nickel can tell you how did I connect? How did Nickel connect each and every GPU here? And here's a sample where Nickel does a connection via a ring. Can also use different topology, but it can be of interest to debug it. And here you see something which indicates InfiniBand. And this is actually what the underlying technology is, what was connected to bring those two systems together. So externally, the extension to NVSwitch is basically InfiniBand, or RDMA technology like RDMA over converged Ethernet. So if you go into the big jobs, at some point you will run into that one. Right. My validation loss is too high. You might run into this one. Yesterday, Adam showed you this graph. I'm using it in this deck as well. Just to recall, it kind of feels like overfitting. There are recipes to bring you back on the convergence corridor what you're used to. LAS is one of them, and warm up is another one. In my domain, in automotive, people want to be able to reproduce it and the results for each and every run. So they love basically technologies which are deterministic. Another, yesterday you've heard a comment from the gradient noise, which depends on the complexity of the data set, determines the convergence and the scaling limits. So you could think about using asynchronous methods rather than synchronous methods for the data exchange, but those are not in focus here. So here we only focus on deterministic approaches, and we have learning rate warm up, LAS and LARC, and some use basically a deterministic gradient noise, but I don't see that very often. Academically, it's not fully understood. Adam pointed it out yesterday. Do I have a large mini batch issue? Well, you can find out simply. you can simulate smaller mini batches, but keep your multi-GPU setup. Right, you do everything the same, but you artificially turn down your batch size, and then you should basically be on the corridor what you're likely used to. So and then you can compare it, and then you see if it has to do with the mini batch. So that is one of my basic methods to find it out. Learning rate warm-up is to start gradually improving the learning rate. I did a hand figure to it. My favorite way of telling it is start eating faster slowly. So in the beginning, some have a step function, some do linearly, but you use a couple of epochs for the warm up. In many samples, I've seen 5. In some other samples, I've seen 30. Then you keep the plateau, and then you usually apply a decay strategy of your choice. So that's essentially it. If you go into Keras, you find a learning rate warm-up scheduler straight out of the box. I think in the meantime, most frameworks have it. Kind of all projects in the meantime make use of that one, I would say. So that is a little procedure performing the warm-up for TensorFlow. At that time, it was not there, but it's not to implement it. It's not rocket science, right? Then you hook it in, and that's basically it. So it's easier or it's more convenient in Keras. I think I need to check if it's there in the meantime. Likely it is in some contrib frameworks. So not a big deal. This is with regards to Lars. It was introduced yesterday, and LARC, basically control and scaling and with clipping. And the basic finding, to repeat this from yesterday, was some the colleagues, you have them, Boris Ginsburg was one of the main guys in here, and Joel Gidman. They found out that when a gradient update is in its magnitudes much higher than the gradient, the weights, not the gradient, the weights, then they think that is indicating, that can indicate a problem and a divergence. And so the observation, what they did was, whenever this is going to happen, they say it's better to do the right scaling of those, and then the convergence is better. So that's in essence what this is. It's also in the frameworks nowadays. It comes in the form of another optimizer, and here in line 127. Here I was consuming it from one of our packages, NVUtils, but you find it in as a standard recipe now in I would say kind of all frameworks, and you apply it after the other optimizers. Don't be confused about this loss scaling optimizer. That was due to mixed precision, so you can ignore it for the moment. I was asking my colleagues, say, what are the best recipes you're using? And then I got a couple of interesting advices. And the first one is, if you have a more complex workload, make the density in the fewest amount of system as high as possible. So If you need to go, it's better to use basically 2 8-GPU systems rather than 4 4-GPU systems. That's logical because there is some communication inefficiency, and that is because of that. So consolidate it to the fewest amount of systems you can. Then regarding the learning rate schedule, cosine and poly Adam, help me. The poly decay, I only have it at the top of my head like this, is what they recommended me to use as a learning rate schedule. This does not mean this cyclic learning rate. There is one paper in the context of cosine learning rate decay, which is doing a cyclic character. So just to make sure that it's not this one. The other recipe, what I was getting was use luck. You cannot do something wrong. And Lars. So there's no harm with it. There's no drawback. Then a source of good implementations were recommended to be MLPerf. However, sometimes MLPerf implementations can be also a little bit difficult to understand. So those are very sophisticated implementations. I've heard that longer warm-up period is definitely something which is recommended to make sure it's running stable and converges nicely. Number 6, do not apply Lars on batch norm layers. Well, it's kind of almost intuitive. And then weight decay was also meant to be a good recipe to keep basically the weights under control. Regarding learning rate, can grow linearly with the batch size. That was basically I heard that the most often. But with higher learning rates, use extended warm-up periods. So with more GPUs, use more extended warm-up periods. Also, a small advice on how does batch size depend together with the learning rate, and the learning rate schedule also is mostly seen as a function of the batch size. So the higher the batch size, then delay the learning rate decay schedule. The 1.2 was given like a number which I averaged. I received several responses on that one. Learning rate can be pushed much higher with layer-wise adaptive optimizers, and like LAMP, Novograd together with Lars. And so that tells us always use those, because then you have the best chance to finish your job early. So I found those recipes kind of helpful, because before that one I looked into a couple of implementations which are out, which I found on GitHub, and there basically the learning rate warm up and Lars Lark was the most used profile. But I couldn't derive basically those experiences from the colleagues from those samples I've seen. Which optimizer was scratched yesterday? Also, Adam is still popular, but the new kids on the block are Novograd and LAMP, I would say. in my best experience, I've done it with SGD in large mini batch settings. So when it's a good combination still. Here is the reference and to the paper of Novograd. I think I have seen it in. I definitely have seen it in Keras. I was using it lately in the PyTorch setup, but I don't remember where I took it from. In academia, there's another idea which says you can also try dynamic batching. I want to try it, and here's a sample of a dynamic batch loader in TensorFlow. I couldn't repeat the same experience. So the idea is here to start with smaller batch size and ultimately change it, but it's implementable. And you can change the batch sizes on the fly, more or less on the fly, with TensorFlow. And here's a sample. So you basically make the you make a batch size parameter, a parameter you pass into the graph, and then it is able to adjust the pipeline and get more frames or other batches out of it. Works, but I haven't come to the conclusion that it helped me. The other recipes are good enough. When to use what? Horovod or your favorite parallelization method, be it data parallel, for example, in PyTorch. It's always good to use it from day zero, and data sharding. Those are the two mechanical elements you have to do. And I advise everyone, when you start a new project, put it in. Most often seen in GitHub projects, I've seen learning rate, the warm up, and the decay, and the application of Lars and Lark. For your experiments, we advise Novograd and LAMP to test. And that is actually what I wanted to share with you as practical recipes for what Adam motivated theoretically yesterday. I hope the repetition of the concepts helps that you settle them. I hope I could motivate you to use it right from the start. I have a bit more on how to work with bigger jobs when you want to run it from an infrastructure point of view. But I think this is a good time to have a couple of questions and answers.
So in chat, I don't think we had anything. There was some Zoom conversation, but that's not related directly to what you're doing right now.
All right. Then I have kind of 10 more minutes on the orchestration of it. And this shows you how simple it is to work with this this paradigm, what we showed with Horovod. But the other one is the same thing. The data parallel in PyTorch follows the same logic. So how do the trading jobs look like? The trading jobs for my colleagues, our colleagues. So I basically say single GPU code is a dying species. Because we are fully on that train that we use multi-GPU jobs all the time. Horovod, what you learned, runs well on a single GPU, runs well on multi-GPU, and even more on even bigger systems. So it's kind of the rubber band. It runs well on your desktop, it runs well on the cloud, and so in my opinion, those are the pervasive training jobs, in my opinion. This is the thing which kind of runs everywhere, makes the best out of the infrastructure. And what I like the most is it is one code base, right? Many CIOs were telling, this new deep learning and AI stuff, it's a pain. Some guy wants to have exactly 2 GPUs. Most guys want 1. I don't know what to do because often the consumption of the resources was hard-coded in the training job, and Horovod does not force you to do it. So it's one code base for kind of everything what you have. And one paradigm for all the frameworks as well. Right, Adam talked about this one. Now, how does it look like from an orchestration point of view? We recommend to use NGC containers. Usually I ask if everybody is familiar with NCCL, with NCCL. Most people aren't. Most people have installed CUDA drivers, lib, QDNN, but NCCL is important and most people are not used to it. So if you want to have a bulletproof container, NGC brings it all together, brings Horovod bundled in, for example, brings data parallel bundle in for PyTorch. It's just there. Also, the MPI tools are just there, so it's a good way to start. And then where we stopped yesterday was saying we showed Horovod run, we showed MPI operator or MPI run to start a Horovod job. So essentially, on the command line, you have seen how to run a job up to this level. The jobs you've seen were using MPI run or Horovod run and basically using the NGC container down below. You can install it by your own, but in essence, those who need to orchestrate it, they see an MPI-based interface from those jobs. And then you have the choice to say, how can I orchestrate an MPI-based job? And you have the choice for example, for Slurm or for Kubernetes world. You can do both. Here, I'm stressing this rubber band characteristic again. I was saying this is one code base. It's just the way to parameterize how big this job is. So here I was explicitly typing out the numbers to characterize the job. So we are all on the same system, right? We have all the GPUs we're using on the same system. We say 2 processes. And all the processes, all the 2 on localhost. In fine print, I made a couple of details. You can ignore them for now. But at the end, I wanted to run my mixed precision example here, which is multi-GPU at the same time. To run the same job in a different setting, let's say I want to use 8 GPUs, given that I have them. I exchange the 2 by an 8. Right, that's about it. Now you get the gist of it. Let's go beyond a single node. We talked about the sample yesterday as well. Let's go really big, or fairly big. 24 towers, 10 to 24 GPUs. Now we need to tell it where this workload is going to happen. But in essence, you see it's the same thing. It's just a question where you put the infrastructure and the resources in to make it run right. And here I'm going to visualize how this could look like on 3 systems. So in the beginning, you remember we had an architecture. I hope you can see it. We had an architecture of a DGX system with 8 GPUs, 8 CPU, and its networking. Now we have on the left basically 3 layers of that one. And then let's say we want to have a big job across all those. So those are the red boxes in here, and they are connected using nickel essentially. And essentially, if you look into our so-called pod architectures, you all of a sudden see that this is the way we build bigger clusters out of those. So we could go in more detail and say, okay, how are those systems connected? They're connected via nickel. Those rings are built. What I want to tell you now on that one is bottleneck can be is something you need to have in your think about at some time. Likely not now, but if you extend your data center a bit, then it comes at some place. For example, we have this 24 GPU job before. Each one has its training pipeline, and that simply means that each one of those processes is demanding for data, and they are crying, "Give me data." So that is the thing which motivates caching on the system and motivates having a look on the data on the balance of the system. Right. We can automate this one, and you have the choice to do it with Slurm or with Kubernetes. What is happening behind? There's an SSH secret generation. In the meantime, this is also described pretty well, which brings the container together. They are in a standby till the process number 0 is able to talk to each of them and basically start the training work. So that is basically the model behind running the same processes on multiple systems. So that is with regards to orchestration. I guess you find Slurm very convenient in case you want to enable it. Others do Kubernetes, as said. This is what I planned for to tell you about the orchestration. So again, MPI is the connection between the two worlds. It fits nicely together with orchestration. So it's a good, well-adjusted package, I would say. Good. That is what I had in mind to share with you about today. Any questions?
Yes, please go ahead. Anyone, if you have any question, please do. In the meantime, I actually have a questions regarding MPI. Mm-hmm. We have this system running Slurm and do not MPI install on the host system because we run the Slurm and Singularity image. What could be the similar setup that can make use of multi-node setup if we do not use MPI directly?
What is worth to mention here is that we use the MPI distribution coming with the container.
Yeah.
So we don't use an MPI installation on the host.
No.
And so when you decide to use Hoverwort and you install it via the pipway, then it relies on an MPI package in the container only. So there's no dependency on a host installation, which is convenient, which I find very convenient. And so I don't see there's a dependency at all.
No.
So you can use it straight. You don't need to think about MPI distribution, etc.
So user, if they want to run multi-node jobs, then with the correct image, say Docker or Singularity image and Slurm, they can start a job.
Yeah,
And
definitely. So with Slurm, they request resources, they deploy appropriate containers to appropriate nodes. Those nodes then need to be able to receive communication. So typically they will have to have additionally an SSH server and passwordless communication configured. Then you go to one of the nodes and all of the Docker containers already have MPI installed. And then you just execute MPI run, point them to correct containers, and they do their thing.
So when this topic comes up, you're welcome to reach out, so my personal goal basically was for the audience in here, if you haven't done it, do it, make it part of your standard deployment paradigm, because I'm convinced you'll like it, because your projects are getting done quicker, your papers are finished earlier, so just use it, and then gradually your demand will go up, and then but I am very sure that you find immediate benefit and pleasure in doing it with your projects. So that's my basic goal. If you use 2 or 4, just get started, and then you make your experience, you get your intuition, like you've done for the project you've done already, right? You develop this intuition. This is a good learning rate to start, and so make it part of your default behavior. We've showed you how you can extend this into the madness, so to say. But you will not start in the madness with that one. But you will develop your appetite, and the appetite comes while you eat.
We are having currently 2 DGX tools that connect to this in a mini cluster, traditional clusters, and also are planning to add more the nodes which are not DGX2. I think they use T4 GPU cards. So yeah, I think for now, for 2 nodes, and we have more than 100 users. So the available GPUs per user is not that high. So do you still advise that they can try this? And like instead of running several GPUs on one node, then they can spread out to 2 nodes or more later.
So I need to drop in a few moments, but I think if you look into your code and your user base, you'll find a different types of profiles, and you find those who are more greedy than others. And as a university, I think today there's a competition about bringing the best papers, and that has a dependency on what is the environment. It's like a DGX is like the laboratory for a chemical guy, right? Without a laboratory, they cannot do anything, and you need to give it what they ask for, what they deserve. So I would say yes, you will have some who do it, and some who stay in the paradigm they used to it. I would deploy it, really, and maybe somebody says, okay, today the system is occupied, but I know how to run the same job somewhere else. Maybe a friend has a bigger workstation. Maybe they got a voucher from AWS, which they want to burn down. And so it is. I recommend to do it. Yeah. So I need to drop off. We coordinated yesterday. In case there are more questions, Adam has a few more minutes,
sure.
if that's okay. Yeah.
Yeah, I'm at your disposal.
Thank you very much, Wang, for inviting.
Thank you. The same
We are
here.
here and we are solving your questions. Also, the students and the audience, you have the addresses. Please reach out. Don't hesitate.
Yes,
Yeah.
that's great.
In the meantime, any questions? Anything that you'd like to discuss? Clarify? Share?
I mean, please, anyone is in the room, take this opportunity and ask the thing.
So I do have a question.
Yeah,
Yes.
Alexandro, please.
Hi. I was not here today for the first part of the meeting because I had an overlapping with another one, so I'm not sure if you already covered this. But I was wondering, that's nice that this framework for parallelizing in several GPUs. But I have a main concern because recently a lot of there is a lot of attention on graphs, for example. So when you want to classify graphs or doing something on them.
Yep.
So I don't think, I mean, I'm not sure if I quite understand correctly, but can you apply those techniques on graph? Because typically you have, if you have to consider the full adjacency matrix, how can you split it? How can you, for example, do message passing through, I don't know, graph convolutional network? Can you do that? Or
yeah, so Horovod will not care about the structure of your neural network. So if it worked correctly on a single GPU, it will just work on multiple GPUs. So if you're dealing with graph neural networks, just Horovod simply doesn't care what is your implementation. If you run out of memory on one GPU and implement it in a model parallel way on two GPUs, again, Horovod will not care. What it will do is it will make sure that it doesn't create unnecessary communication. So certain parameters are only on GPU 1 in a group of 2. It will make sure that those parameters are copied exclusively to GPU 1 on other data parallel systems. Also, if you're working a lot with graph, not necessarily with graph neural networks, as part of no, you don't work with
non-neural, but not necessarily graph neural networks, exactly.
Yeah, so
graphs, but
so do check out our library called cuGraph. We've executed it's effectively a library for classical graph analytics, and we've tested it on systems like Summit. So again, 27,000 GPUs plus, and it scales very nicely as well. And if you're working with utilities like Network X, you'll be very pleased because you'll see accelerations sometimes as high as 20,000x, 100,000x in comparison to your CPU implementation. So do give it a go.
Yeah. Thank you very much.
Yeah. GPUs are very comfortable with graph processing, so this is a particularly suitable workload for them.
Yeah, I was a little bit preoccupied whether if your input is just a big adjacency matrix with model a very big graph.
No. Horovod expects a bunch of of parameters. Yes. So TensorFlow, PyTorch mark those that are differentiable. And Horovod, the only thing it does, it makes sure that it effectively can exchange and average them out.
Okay. Thank you.
Sure, no problem.
Okay, and before I forget, please, Adam, and also could you ask or send the words to Adolf that
to send the materials.
Share the slides.
Sure.
Yeah, sure.
We'll do that immediately.
Yeah, and then I will pass on to the attendees. Yeah.
Will do.
Yeah. Any thoughts and also how do you I mean the question for everyone's in the attendance, How do you think about these events? Did you learn something interesting from this event? Please open the microphone if you want to say
People are shy.
Well, definitely yes. I mean, yesterday I attended the full meeting, and yes, there are something new that I didn't know. For example, I missed some details. I mean, I didn't know the details about the lamp gradient descent. Let's call this way. So I think that at least was something new for me, which I didn't really know about it. And yeah, I think it was nice also for the robot, which I didn't know about it. I was actually using the in TensorFlow, for example, the mirror strategy that is
Yeah, sure.
inside TensorFlow.
Yeah, TensorFlow team is largely copying Horovod for that implementation. So and I'm not kidding, and it's new. It only came in at TensorFlow 2. So
yes,
slowly but systematically.
Yeah, that's true. It was a nightmare before to do parallelization with TensorFlow because
and
I
it's
started
currently only on.
Yeah, I mean, I was just concluding saying that, of course, it was a nightmare in TensorFlow 1 to do that.
Yep. And even now in TensorFlow 2, you can only scale within a single system. So there is no implementation for multi-node training.
That's true. Yes. Yes.
That is why whenever like Google reports scaling results, they always report Horovod based.
Mm-hmm. Yes, true. But mainly because I think, at least in the university environment now, it's true that we have three clusters, so we don't have so many options. So typically you use only one. But yeah, I think it is good to know, because if at some point we scale up a little bit, then we are kind of ready and know how to handle this. I think it was constructive at least.
Yep, but you're right. The mirrored strategy is implemented also with Nickel. Recently, they've also introduced a gradient compression, I think, and batching. So on a single node, it will now largely work like Horovod. Yeah, I think so.
Yeah, there's two comments or answer on the chat. That's MSA and David both mentioned that the Horovod is very interesting thing that they could learn something about, and the background about the large data and large data modeling is also interesting.
Yeah, it is fascinating, isn't it? And until we find a totally different way of doing things, this direction seems unavoidable. And even intuitively, if you think about it, even all of the living organisms, our neural systems are heavily over parameterized. So we have much more neurons in our brains by orders of magnitude than the number of seconds that we live. So if there was an easier way, I would hope that nature would have found it by now, but it doesn't seem that there is. So no one knows how to do it in a better way.
Well, I mean, the structure of the neural brain is a little bit more complex.
Yeah, sure, definitely. Yeah.
But
by orders of magnitude, yes.
Yes, I tend to agree. But there is another problem that there is a huge difference between neural networks in general. I've been working with neural networks for more than 5 years, so the main differentiation is that, of course, to people are more like one-shot learner, right? While neural network has to see again and again data.
Are you sure of that? I'm observing my children as they grow up right now, No, they are not one-shot learners. People, I think that's a misconception. People become one-shot learners once they build very, very, very solid representations of the world surrounding them. So you become one-shot learner within a discipline that you know, that you have extensive experience of. So I'm not a neurologist. Jürgen was like,
no, me neither. Me neither. Me neither.
If I show you a single image of a brain tumor, will you be able to find brain tumors? No, you will not. But if you're a student with extensive knowledge of brain anatomy, if I show you a single picture, yes, you will understand the concept very quickly. So I think humans are one-shot learners to the same extent that neural networks are one-shot learners. Namely, if you have very, very good representations built, you can start learning quicker. But
that's true. That's true. That's definitely true. Yes, I agree with that.
I'm trying to teach my son how to read right now, and I can assure you, people are not one-shot learners.
Maybe we don't need thousands of pictures of cats to recognize a cat, right?
I think you do. So, like, if you look how a child that is 1 year old, how it learns. If you show him a picture of a cat, you show that child a picture of another cat. It's not obvious that's still a cat. I think we do. We need billions, not thousands, but billions of pictures of things to learn. We just don't remember it.
If you count the rate of image acquisition of things you do every second, then maybe it is more than 1,000 of images.
Yes, in that terms, yes. But I think the main difference is that the neural network don't have any observation of
the prior world. Yep. And in fact, OpenAI did some very cool experiments where they took a simple game, a game that is trivial for a typical human to play, a game where people don't need any training. So I think it was ladders, and they just randomly changed the textures. So normally in a game, you would have ladders, you would have stages, you would have keys, you would have logs, and you would instinctively know what to do. But then they just changed it with random gibberish. And I can assure you that no one is able to play that game just within a single shot. Even if you tell them, okay, from this now on, this random patch of texture is a ladder to play. It's not that simple. We underestimate the complexity of what we have done between the age of 0 and say 16. Yeah. So 16 years of huge amount of training.
And pruning also.
And pruning, yes, because there is this thing called juvenile amnesia. I'm not sure what I'm translating from Polish correctly. So the brain between the age of 8 and 12 will deliberately throw away information. It's a known psychological effect. That is why we remember so little from our childhood. It's the key fact, most critical events.
I see.
So the other day I was watching some documentaries about some people who can remember every second of their life, and some, I mean, there are a couple of them. Some things that is a bless, and the other things it is a burden. Yeah. So, I mean, if they feel that there's too much information to retain and make it inefficient to use the brain or make use of the information, then it is a burden.
Not many of those people are sane. Bear it in mind.
No.
Yeah. Majority of them have severe problems. So. Yeah, so it's a fascinating topic. Let's see how it all evolves. What we've been trying to share with you is current thinking, what the next 6 months will bring, what the next 5 years will bring. I don't think anyone knows that. And people that claim to know that, I'm not sure what they are true. They are honest. There's too much change right now.
Yeah. There's one comment, and I agree
sure.
from Usama that it was a good introduction. I mean, the presentation you did yesterday, it is a complex topics, but you delivered it very well, I think.
Thank you, Candy.
Personally.
Yeah.
Yeah. I think if there's no other comments or questions, I think I would like to point out that I put in the chat box the feedback form, and please use some minutes. I have 6 short questions there, and we would like to get the feedback from you and organize to make the series even more interesting for you. So we do, the idea is that we do this every month, and the length probably depends. Sometimes it's 2 hours, but if it is something like hands-on workshops, then probably we will do it longer. So anything, speak out your heart. If you have anything that you feel that you want to learn more about, some AI frameworks, some tools, or some topics, research topics or something, then please let us know. And then we will try to find the speakers or instructors for you. And yeah, it doesn't have to be like you are from Aalborg University. I think mainly this is for Aalborg University researchers, but if you are interested in attending this series, so it is also open for everyone. Yeah. All right. I think we can.
Okay, outstanding.
Yeah.
Thank you kindly.
Thank you, Adam. It is a great pleasure to have you with us, and also Adolf. Please send thanks from us.
I will do.
Yeah. And I mean, I feel that it is really lucky that we can get hold of both of you and present the topics in depth. And I made the recordings of the presentation, and I will share to the users so they can, I mean, revisit the topics and make use of the information later. Because I think some will be able to use right away, some will need more hands-on experience, so later come back and make use of the information you present.
Yes, do check out that GitHub repository that I've shared yesterday on the slides. I'll share the slides, so you'll see.
Yes, I will send out the slide to everyone.
Thank you kindly in that case, and I guess have a great afternoon.
Thank you, and you too. And to everyone, thank you for attending, and see you next month.
Outstanding. Bye.
Bye.